Good afternoon, everyone. Thanks for coming. Like Leah's introduction, I'm here on behalf of Raymond and his fellow co-authors, unfortunately, who cannot be here today. I'll be presenting their paper on the topic of model hijacking attack against text generation model, which is a collaboration between CISPA and Microsoft. So let's start with what is a model hijacking attack. So in a standard machine learning pipeline, the model owner trains their model for a specific purpose, such as classifying an image or text using data like MNIST or SST2. However, recent work shows that it is possible to take control of a target model and force it to perform a completely different task. For example, researchers have demonstrated that the ability to hijack a model trained with CIFAR10 and compel it to perform the MNIST classification implicitly without jeopardizing the model's utility on CIFAR10. Similar to data poisoning attacks, this attack requires poisoning the training data of the target model with the transformed data set. But under what circumstances does the adversary have the chance to poison the training data? So at this moment, we all know that deep learning has significantly improved the performance of various tasks, but this has come at the cost of significant increase in the required resources for computational power and data sets, especially as these models are getting bigger. So as a result, various training paradigms have been proposed to alleviate this need for computational resources, such as federated learning. Similarly, it is common to crawl data from the internet to alleviate the need for larger data sets. Both of these actions can potentially provide the opportunity for the adversary to contaminate the training data. So in this paper, they apply the model hijacking attacks on NLP models. Additionally, they extend the attack from hijacking the classification model to the generation model, which is more popular these days. So before going into details, let me show you an example of their attack. So let's say we have a summarization model that take a long paragraph and generate a shorter summary. So as a regular user, suppose we want to summarize a movie review, we use the model and obtain a proper summary. If we look at the output here, it appears fine, and we can see that some important information from the input is kept. Before the adversary, however, the output actually means more. In fact, this input is coming from a sentiment classification data set, and the adversary can determine the sentiment of this input by looking at the output, which is the hijacking task. Specifically, these highlighted tokens are the pre-trained signals used by the adversary during the poisoning. Then they can check these signals and determine the label in the deployment phase. Later in this paper, they demonstrate that this method is effective not only on summarization, but also on translation and general language models to some extent. But so what are the consequences if the attack succeed? So first of all, it would raise the accountability risk. So for example, an adversary can hijack a translation model to implement a toxicity grading model, which can be used to guide the generation of toxic content, and this could be used unethically. Additionally, an adversary can host a public competition using the hijacked public model, which can be both illegal and unethical. As a result, the model owner might face the blame for hosting such a model. Second, the hijacking model can raise the issue of parasitic computing. So nowadays, model owners need to pay a certain amount of fees to maintain their models online so that the user can access them and use them. However, if the adversary hijacked the model, they can provide their own service without any additional fees. So now, to make this attack succeed, they define two classes of requirements. The first one is performance, which means the attack should not jeopardize the target model's performance on the original task. Additionally, the hijacking model should generate the proper output with the data from the hijacking task. As demonstrated in the example we just showed, for instance, the summarization model should produce a proper summary instead of generating the label directly. And the second one is stealthiness, which means we want the data to be transformed so that it looks similar in terms of the structure to the original data. And when the adversary injects it into the training data, the model owner might not distinguish it from the original task data. So now I'll present their attacks in details. So first of all, they split the attack into two phases, namely preparatory and deployment. In the preparatory phase, the adversary constructs the transformed dataset based on the hijacking dataset using Ditto. This dataset have the adversary's hijacking task features while being hard to differentiate from the original one. So to prepare the transformed dataset, the adversary needs to consider both the input and the output. Regarding the input, existing works in prompt learning has showed the possibility of cutting down the prompt. In this paper, they borrow the idea and get rid of the trigger in the input. However, for the output, a challenge arises due to the difference between the expected output for classification and the output for generation. So for example, the output for a classification is a single label, where the output for generation is usually a sequence of tokens. Therefore, if we need to add classification data to, let's say, a translation training dataset, it is going to hurt the translation model's utility, and the model owner would also notice it. To overcome this challenge, the adversary first generates what they call pseudo-sentences for all the inputs in hijacking datasets. This is accomplished by utilizing a public model. Let's say we want to hijack the English to German translation model. The adversary can use a public translator like DeepL or Google Translate as their public model to obtain the proper output. And now for the hijacking task. So we have the input, the label, the proper German translation. So the question is, how can we combine the label and the German translation together? So first, the adversary constructs the hijacking token set for each label in the hijacking datasets. For example, if our hijacking task is SST2, which is a binary sentiment classification dataset, then we'll have two hijacking token sets, one for positive and one for negative. For each set, we predefine a set of stop words tokens in German, since the target model is English to German translation. We treat these tokens as indicators, as they will be used to map the hijacking model's output back to the hijacking task label. So then, the adversary can start to embed each pseudo-sentences with tokens from the hijacking token set, depending on the label. To make this embedding smooth, we use a masked language model like BERT. In details, we can either replace or insert a new token that comes from its corresponding hijacking token set with the help of BERT. And we repeat this process multiple times for each pseudo-sentence until the sentence semantic deviates too much from the original, or after just a certain set number of iterations. So at this point, the adversary has transformed the dataset and ready and wait until the model owner uses it. So once the model is successfully hijacked, the adversary can extract hijacking results during the deployment phase. So to accomplish this, the adversary first queries the hijacked model with the input from the hijacking and obtains the output. So next, the adversary extracts the stop words from the output sentence. So we can look at the previous example again. So the adversary determines the hijacking result by comparing the output sentence and the hijacking token sets. You can think of it as a naive approach, is to compare the number of stop words from each hijacking token set and select the label with more stop words in the output. So for example, if there are more stop words from the positive set, we classify it as positive. There are more details in the paper, including details of replace and insert operations and the objective function design. So feel free to check it out. Now I'll be presenting some of the results for the attack. This is attack results on hijacking the translation model with different classification tasks. And so first, we want to check the utility, which is the translation performance on the original data. So as the figure shows, the drop in utility is largely negligible compared to the non-hijacked model. This shows the hijacking attack does not jeopardize the hijacked model's utility. And second, we want to evaluate the attack success rate, which measures the performance on the hijacking task, which is a classification accuracy. So the performance of the attack is strong and clearly beats the random baseline. And moreover, it is comparable to the performance of a fine-tuned BART. So lastly, we want to check the stealthiness of the attack. So ideally, the output of the hijack model should look benign when queried, no matter using the hijack or the original data. So to this end, they use the same metric presented in utility and evaluated the stealthiness of the hijack models. So as the table shows, the performance of the attack actually varies with respect to the used hijacking datasets. They suspect that happens due to the difference between the original and the hijacking data property. And more details can be found in their paper. So they have more studies in the paper, and just feel free to check them out. So to summarize, the paper presented the first model hijacking attack against NLP models. In this attack, the adversary poisons the training data set of the target model to hijack it into performing different tasks. Although the original and hijacking tasks are significantly different in structure, these results demonstrate that their attack can hijack translation models while remaining stealthiness and achieving strong performance. So this new type of attack can cause accountability and parasitic computing risk, as we've discussed. So their experiment shows that their attack can efficiently hijack translation and summarization models. So that's all for the paper, and the code will also be released soon. If you have any questions, I can try my best to answer them, but also just don't hesitate to send them an email. Thank you.